Now we're going to start down through and look at our single cylinder misfires as well as multiple cylinder misfires. Now we're going to start with our primary ignition. We could have started other places, and you can jump to another part of the program if you want to start with fuel delivery, fuel control. But let's talk about the ignition. Now we're going to show you a lot of patterns as we go through here. What we recommend is that you make a recording and play it back frame by frame, or at least freeze it so you can study the details. These patterns are sometimes happen so quickly that it's difficult to see them on the scope display. And you need to understand the ignition first, because before we start talking about this particular part of the pattern or that particular part of the pattern and the problems they cause, we need to understand the nature of the problems. So we're going to start with ignition coil basics. Now the ignition coil is a transformer. It's a step-up transformer. It has a power rating. It's going to transfer power from the primary over to the secondary by using magnetic coupling. And it's 98% efficient, which means we have a 2% loss. And that's not unusual. But let's start by looking at the drive power. Drive power coming in is 14 volts at 7 amps. Now power is voltage times amps. So that gives us 98 watts. While on the other side, we have output power. It's 98 minus 2%, which gives us 96 total watts. If the secondary resistance and spark gaps require 14 kV in order to get a spark, the amperage of that spark will be 6.3 milliamps. It's milliamps times volts to come back to the same 96 watts. It's the same situation. What we have in is what we get out. Now that's an important thing to understand, because the secondary is a power limited circuit. It is powered by the primary. If something goes wrong, it's a problem. The voltage in the secondary also controls current flow, because if we have resistance in the secondary where the voltage requirement is way high, like 40 kV, we're still power limited and current will drop to 2.4 milliamps. That's what we mean by a power limited circuit. As the voltage increases, we have less current flow. We have a weak spark. We're also going to wind up with a weak spark if we have a situation like we have here, where we have low input power. In this particular case, we have 14 volts at 4 amps. That gives us 56 watts. This low current is going to result in a weak spark on the output side. Now let's take a look at the output side. We have 56 watts minus our 2% loss. That gives us a total power of 54 watts. At 14 kV requirement to get a spark hasn't changed. The secondary resistance is the same. But as a result, the low current in the primary results in a weak 3.9 milliamp spark. What we're making a point of here is you've got to test both the input and the output. Low primary current or high secondary resistance can reduce spark current, resulting in a weak spark, which is how we get a misfire. Now, you can pick either side you want to start testing, but we're going to start testing the input side with a low current probe. Now, a low amps probe is sometimes faster to connect than the secondary adapters, and we want to make sure you understand that. We're going to start with the low amps probe and talk about it, utilizing it with a digital storage scope, because we need to see the pattern. But let's talk about this low amp probe and what it does. It produces a low voltage signal by detecting the magnetic field strength produced by current flowing through the wire. It is converting this into millivolts. Now, if you have a low amps probe designed to work with your lab scope, and you have a lab scope setting for low amps probe, you will read this out as amps. If you're adapting a low amps probe to another scope that it wasn't made for, you're probably going to have to set a millivolt scale and use the scale on your low amps probe. It will tell you how many millivolts per amp you're looking at. And that's the way you're going to make a measurement. Let's look at exactly how we're going to connect this low amps probe. Now notice in the upper left, you can see the Hall effect pickup, the low amps probe, connected around the pink wire. We're going to detect the magnetic field about that pink wire. And looking down at the arrow, it's pointing to pin P on this DIS module. This is the module's B+ supply. It's coming directly from the engine control fuse. We want to take you deeper than just the elementary stuff like this. Let's go even deeper into how this operates. Now, as you look down to the right, this happens to be a module that has 3 plug-in coils. There's one of the coils on how they plug in and pick up the B+ and ground supply. What we're doing is we're measuring current on this pink and black wire, in this case, coming into here. Notice that this wiring connects directly to 3 separate primaries. This is a 6-cylinder engine, so what it has is 3 primaries, each primary firing a series of spark plugs. So when we look at this one signal up on the pink wire, pin P, we're going to be measuring current for all 3 coils. Now, this is something we do without thinking about it very much when we're talking about DIS. We frequently forget doing that. We get to coil on plug. We keep thinking, well, we can only look at coil on plugs one at a time. Not so. If we take a look at the diagrams like this one, that splice 162 circled in red with the pink wire coming into it. If we're on the left side of that splice, before it separates to go to coil 1, 3, 5, and 7, we can look at all 4 of these at one time. Now, this takes a little more work sometimes because locating this splice is not always easy. It's buried in the wiring harness. But after you've worked on a few cars, you can find out that if you're going to take the time to undo these wiring harnesses enough to get the low amps probe around, which takes time, it might be better to do it one time and look at all 4 together rather than look at them one at a time. We're doing the same thing here we're doing there. We're looking at coil current. Now, these are coil on plugs. We had DIS. We're trying to show you we're doing the same thing. Now, let's talk some more about this. All these connections we talk about, we've mentioned it for years and years. I don't know how many times we have solved problems by saying coil is low. Let's start off into the routine checks. Let's check so we got good contact. Look at this corrosion on this particular connector. This is just something we found one day on a car that could not be fixed because it had a misfire under load. I wonder why. Now, don't get sidetracked because there's another ignition here. This ignition signal goes over to pin C of the cam and pin D of the crank sensors. This ignition is not the supply. It is not B+ for the module. No, it has to be on pin P because N is being supplied from the module to the pickups. It's the pickup B+. Just throwing that in so you understand it. But let's look at some other variations, things are happening here. We're going to take this particular module and it's going to create a new signal called crank reference. A 3x crank reference in this case. 3x because 3 times every engine revolution, it's going to have a signal. And these 3x signals are going to be used to control the current in those 3 separate coils we're looking at. Now let's go a little deeper into that. This module uses an 18x signal and a sync signal to create this 3x signal. There's the 3x signal on the scope, and it's going from pin D over to pin C18 on the PCM. That's going to be used for ignition and timing control for fuel and spark. Here's another example. Slightly different vehicle. Same type of arrangement. Instead of having an 18X signal, we got a 7X signal down here at the bottom. Notice this crank signal goes in to the module electronics. Then the module electronics are going to work on it and produce a low rate crank signal, our 3X. This is going to be used for timing our spark and for determining the width of the spark and timing our injection pulses. Also on this vehicle, at the top up there, we have a 24X high rate system. This high data rate crank signal is used for improving timing at low speeds and for doing misfire detection. But let's get another layer deeper and examine this more. We've talked about that 7X signal. That 7X signal has a signature pattern. This is an 18X, and the signature pattern we talk about is it's wider, it's taller and wider than the other 17 patterns or 16 patterns in this particular case. Let's watch how that's formed. If you're looking at a pickup on a Ford, this is right off the crankshaft. As the crankshaft rotates, the teeth are going to move underneath the pickup, causing a change in the magnetic field, which will be picked up by the pickup signal. What happens is this rotates through like this. When it gets to that double wide slot, we get the taller, wider pot. That is a picture of what's on the crankshaft. That's clearly identifying to the PCM the specific location of the crankshaft. Now, sometimes we need to know more than just where the crankshaft is. Let's take the time to go just a little bit deeper. What we're pointing to right now is we have our signature pattern for our 7X GM. You see two pulses close together. That's our signature. What I'm pointing to right now with an arrow is at the time that arrow is there, the red cam signal is low. If we look just to the right, we're going to see that the cam signal is high at the time we have our double pulse. What that cam signal is doing in conjunction with the crank reference, it's setting up our number one top dead center so we can do sequential fuel injection. And it's going to help us identify number one cylinder for misfire. Let's go in one step deeper and start breaking these signals down a little bit smaller. Here's our crank reference we saw earlier. We take the crank reference, the red signal, and then send it to the PCM. The PCM is going to change the timing and control the signal to achieve the proper ignition timing and the right coil saturation time. This is our electronic spark control, for lack of a better term. Notice this electronic spark control signal is, in fact, controlling the spark. When it goes high, it turns spark on. When it goes low, it turns spark off to build a strong magnetic field up around the coil so it be collapsed to generate a strong amperage in the secondary, as we've talked so much about before. Now, this pickup is set up to work specifically with our scope, so it reads out in amps. Over here on the left, highlighted with the red box, is our amp scale. We are looking at right around 8 amps. We're going from 0 up to about 8 amps. We compare that to specifications. And as we've talked before, if we know if the primary has got the right amperage and the right amount of power, the coil should be able to put out enough power to give us a good high amperage spark, like we talked in the past. It's input limited in the secondary. Let's get down and talk more about this coil on time. Now, one of the first things you're going to notice is some weak oscillations down here. If they're missing, you'll probably have a weak coil. But let's talk about this coil on time. We need to understand how the PCM determines how long to keep the coil on. What is the on time? Where does it come from? We're going to compare coil on time to the crank reference signal. Take you deeper. Now, Doc Knoll and I have harped for years that we should be paying more attention to the cranks. The crank signal is all too critical, and we're going to show you exactly why. Now, here's a high rate system. On the newer vehicles, when we get the coil on plug, we're going to have this type of system. Let's look for the signature patterns. They're here. In fact, there's several signature patterns. We put a dotted red line in here because we've got signatures going on in between the big signatures. But we've got a large signature right here. Notice at the time that one goes higher than the rest is at the same time the cam is coming from right at zero and starting to increase. That's identifying a number one TDC for us. This is important because this particular signal is used on a coil-on plug. We need to do some very fine timing. Now, not all signature patterns are going to show up the same way. This one here in the middle, the cam is always low. We're now on exhaust stroke for number one cylinder. So what we're doing is separating power stroke from exhaust stroke on a 4-cycle engine, and by the time we get to 720 degrees of crank rotation, we have a second cam pulse coming up saying, hey, we're coming up with compression. All of this goes back to sequential fuel injection and coil-on plug selection. Let's get deeper into these patterns and look at something. Here's a crank reference off of our original 18X signal we're looking at. Now, this signal is used to generate this coil control down here. Notice there's 3 of them. We have 3 coils and there's 3 sets of them. But let's look a little finer. Here's where it goes high. Notice how it aligns with that, and then that's where it goes low. That's where coil current turns off and where coil current turns on. It's exactly the width of 3 of those pulses. You think that's a coincidence? Well, let's go back and look at our 7X signal. Here is our crank pickup from our 7X signal. It's up there in yellow. We just got through looking at it, but now we put some different stuff up here with it. Now we're going to look at coil control number 1, which just happens to be purple. And we see it going across there, and there's 2 of them. This is a 4-cylinder engine. And coil number 2 goes across the bottom down here. But let's go even deeper. Look where coil on time occurs. Notice how it aligns itself, and coil off current aligns itself with the crankshaft pickup signal. Now, we're doing this not to show you how smart we are. We're doing this to remind you how important it is to get this signal right. If you think these 2 are a coincidence, take a look at this Chrysler. Here's our crank pickup. It's got a long pulse and 3 narrow ones, and then 4 short ones, and a long pulse and 3 narrow ones. But I'll show you something about how that's working. There's something special going on here. Let's look at where coil current starts. It lines up with that edge of the pulse, and coil off lines up with this edge of a pulse. Now, you just saw it on an 18X signal. You saw it on a 7X signal. Now you're seeing it on a Chrysler. Let's take you a step even deeper into this. Let's take this up to a higher RPM. This is 2,500 RPM. Same signal, but look what's happening. Here's where coil turns on. It's using the leading edge of that large pulse. Now, you might notice something. The large pulse is the pulse that turns all the coil currents on. Then we find this relationship where it turns it off. It's had to start it sooner. This is called spark advance. Timing is advanced at higher speeds. The firing is moved to the left earlier in the crank rotation. Any surprise that why these are grouped into 1 long and 3 short? Interesting, isn't it? Look at this down here. That's our spark. As we go across here, are all those sparks doing the same thing? No, they're not. They're telling me I've got some dirty injectors. They're telling me I've got maybe a bad plug wire. I'm not sure. I've got some things going on down there, but definitely dirty injectors. We have an entire section on that later, but I cannot pass up the opportunity to say, when you look at this, take it up off idle and see what it looks like off idle, where the coil has to saturate faster and work a little harder. The plugs work a little harder. The mixture is going in and out of the cylinders a little faster and has more demands on the delivery of the fuel off idle. So we've talked about the primary and the crankshaft position. I just want to remind you that coil primary current control is directly related to the crankshaft position signal in some way, shape, or fashion. The timing of the ignition firing will be determined by engine load and the engine speed. That's all mass airflow, MAP, stuff we've talked about earlier. But the bottom line is, don't expect normal ignition timing, and don't expect ignition control current to be right if the crankshaft signal is erratic or has excessive noise.